Good morning, everyone, and welcome. For those who don't know me, my name is Dinesh Dulipsingh, and I'm with Lexington Soft. I am actually doing this presentation on behalf of Dr. Enrico, who had to cancel his flight due to health constraints. So I'll try my best to fill in his shoes and go through this topic. The topic that we have today is tackling hardware attacks and strengthening defenses through automated security testing. So before I get started, I'd always like to set some context. And let's take a look at vehicles and this continually evolving landscape. And if you take a step back and look at cars of the past, they were characterized by mechanical components. There was no electronic components. There was no software, and also there was no connectivity. And in contrast, today, the landscape has evolved very significantly. And your vehicle today is a highly connected system. And if you heard most of the speakers yesterday, I think the common theme was vehicles are extremely software driven with a lot of advanced embedded systems. And this incorporates a lot of advanced software as well as your autonomous capabilities as well as your connected network. Also, the cars of today are highly connected and part of a larger connected ecosystem. And with the Internet of Things that enables vehicle-to-vehicle communication, vehicle-to infrastructure communication, as well as integration with the cloud. And then you couple that with automation and AI-driven features like ADAS and autonomous capabilities, it starts to evolve. And today there's a big emphasis on cybersecurity and compliance to a lot of the different standards like UNICE R155 and ISO SAE 21434. So what does that mean? Basically, it means there's a lot of challenges to address in the automotive industry when it comes to testing. And challenges here really is the expanding attack surface. So you have increased entry points due to connectivity, like your infotainment, your over-the-air updates. There's also the need for scalability and automation. And there's also the compliance with regulations. But most importantly, you've got the evolving cyber threats, right? You've got hackers trying to exploit the vulnerabilities of an ECU, compromise the communication protocols like CAN, and essentially breach the security of the automotive system. The only thing here is the stakes are a lot higher today because when a successful breach happens, it's just not compromising your data privacy, but it's also jeopardizing your safety, your reliability, as well as trust. So let's take a look at how hackers really try to exploit the system. And let me just get this going here. I think I had that. So I'll start with the objective of an exploit. So basically, hackers exploit the system and they try to bypass the security mechanisms and obtain malicious code execution on a target ECU. And they can do this in a number of different ways, and the objective is to extract the firmware, reverse engineer the code, and leak the secret keys. Also, the objective could be to enable a censored JTAG interface to make further modifications. Additionally, they might try to reprogram an ECU to install new keys on a stolen car, or it could be chip tuning where they actually change certain parameters to kind of enable features which hasn't been paid for. It also could be enabling features on demand permanently. So there's really a myriad of possibilities, and we'll take a look at some examples of weak cryptography. So most of you might be familiar with UDS. UDS stands for Unified Diagnostic Services, and essentially it's a protocol for vehicle diagnostics. And secure access is really a mechanism which grants authentication to a user so that they can access a vehicle's functions. So, and sometimes UDS security access is the only authentication before code execution. So what we'll do here is we'll take a few examples of how we can see some security algorithms that are weak, and I'll go through a few of these examples here. So here's an example of UDS security access, right? And UDS uses what you call a challenge response mechanism. The challenge is the seed, and the key is the response, right? And in cars of the past, the seed, the challenge, and the key, which is the response, which is used for UDS security access, is often hard-coded in the ECU. So if you look on the right, you see the seed and key. They are a constant. And all it takes is one visit to the repair shop, which is sufficient to get the key. And this way you get access to the vehicle's functions. Moving on to a slightly different example. This is an example of UDS security access where the key is actually the seed negated, and I'll explain that. So here what a hacker could be doing is they could be monitoring the communication between the car and the repair shop tester, and they'll figure out the data that's being exchanged. And then if you look at the numbers on the right, there's the seed and the key, and anyone with any knowledge of hex values can crack this in 30 seconds. The key, as you can see, is really the seed negated. So once you have the key, you have access to the vehicle's functions. Here's another example of a security access which uses pseudo-cryptography. And in a situation, in a situation like this, what happens is the attacker has actually kind of gotten access to the firmware and probably has reverse engineered the code. And basically, once you've reverse engineered the code, you can look at the decompiled code and essentially get the key. And once you have the key, you can gain access to the vehicle's functions. So these are some of the examples of weak security access. And let's take a look at UDS security access with real cryptography like RSA. And I'll try to explain how this works here. So with this situation, you have the public key, which is stored on the ECU. You've got the private key, which is in some backend or smart card. And the challenge here is the seed, which is a ciphertext. The response is a plain text. So how this works is if you look on the right, your repair shop tester tries to access the vehicle's functions. You've got a plain text key in the ECU, which is encrypted with a public key to obtain the seed, which is the challenge. And if this challenge is sent to the repair shop, they decrypt it at their end to essentially obtain the plain text key. And then the authentication happens. If key equal to key, the authentication passes. So typically it's impossible to extract, but is this really secure? Yeah, I guess the question here is it may not be that secure, and it can be only secure if the pseudo random number generator is good. So here's the problem, right? With a weak pseudo-random generator, you've got only 31 bits, so which means there are 2 billion possible challenges that can be generated. And here's how an attacker can actually access the system. So they, in all probability, have gotten access to the public key. They pre-compute all of these 2 billion possible plain texts. And you think that's a big number, but with a laptop, that only takes about 20 minutes. right? And essentially, once they do that, they create a lookup table. So here's how they would hack the system. So the hacker tries to access the car's functions. The ECU has a plain text which is encrypted and sends a challenge to the hacker. Now what the hacker does is they actually take a look at the lookup table and look at which encrypted message actually matches with the plain text. And once you've got the plain text, that's your key. It's sent over to the car, and if it's a match, the authentication is a success, and the hacker gains access to the system. So a couple of other things I just wanted to highlight here is the attacks on cryptographic implementations. There are two kinds of cryptography out here, and one is symmetric, where the key is same on the both ends of the communication. You've also got asymmetric cryptography, which is a private key. And when a hacker tries to actually crack the system here, they try to completely bypass the authentication process. So we'll take a few examples here and see how this works. So how does a hacker recover keys, right? They could do side channel attacks. So a side channel attack actually exploits the physical characteristics of the system and tries to recover the cryptography key. And side channels is typically anything which is not your input data or output data. And this could be your timing information, your power consumption, or your electromagnetic emissions. And side channels will be used by an attacker with physical access to the ECU to extract the keys while they're being used by some cryptographic algorithm. So let's see how ingenious hackers can get to actually break into the system here. So this is essentially how they do it. So an attacker typically will have hardware access to the target, and they can measure the power utilization and the electromagnetic emissions of the ECU. And the ECU is a processor with registers. Each register has a capacitor, and when you flip a value from 0 to 1, there's a little bit of a current discharge. Oops, so sorry. I'm sorry about that. So there's a current discharge, and essentially the current flowing consumes both power and emits radiation, and both of which can be accurately measured. So let's take a look at how this works. So what the hacker does here is they capture thousands of power traces while the target is encrypting payloads with the target key. And in this case, we are talking about symmetric cryptography using advanced encryption system, which is AES, which is 128 bits, which is about 16 bytes and 2 power 128 possibilities. So they capture these power traces, and then what they do is they attack one byte of the key at a time. Why they do that is basically by attacking one byte, it's 2 power 8, so you only have to make 256 guesses for the selected byte. And for each guess, they compute the expected power utilization, and then they apply a correlation coefficient, and whichever guess correlates the most with the observations, that's likely to be the correct key. So therefore, each key byte is leaked with only 256 guesses instead of 2 power 128, and this way they are able to recover the keys. So there are a couple of other ways hackers can actually break into your system, and they use fault injection, right? So what is fault injection? We'll get there. So side channel attacks, like we saw earlier, can be used by the attacker to extract the secret keys from the ECU. But when the keys are not in the ECU, there's nothing that can be extracted. And the objective of the hacker here is to really completely skip the authentication process. So there's a couple of types of fault injection. I'm not going to get into the details. You've got power glitching, body biasing, laser fault injection, and electromagnetic fault injection. With the exception of electromagnetic fault injection, all the other three require direct communication to the device. So this is how the hacker creates a disruption of the instruction workflow. So as you can see, there's C code on the left. Line 3 is actually doing the authentication. And line 7 grants access to the vehicle's functions. And if you look at the assembly code, the equivalent there, the authentication happens at line 7. And the question is, can we skip this step? Because if you can skip this step, then you get access to the vehicle. And that is possible because the way the hacker does it, they have physical access to the device, and with a well-timed crowbar glitch, they can cause this to happen, right? And what happens here is they apply or ground the power at nanoseconds, and when this happens in a timely fashion, the instruction which does the authentication gets skipped, and the CPU fetches 0 because of the fault, and essentially the execution continues normally. So this is how ingenious hackers can get. And kind of looking at another way of disrupting the instruction workflow is here's an example of an assembly instruction which is loading the register R7 from that memory location pointed to by the red arrow. And that memory location most likely has access to a communication interface which is available to the hacker. And essentially what the hacker will be doing is they will be able to place their own code into that memory location. So how this works then is you try to do a single flip of a bit, and when you do that, what happens is the load instruction actually becomes a jump instruction, and the whatever instruction was placed at that memory location is then placed in the program counter, and the CPU starts execution. So this is another way of disrupting the instruction flow. So as you can see, hackers can get ingenious and try to hack your system. And the question here really is, how do you find these vulnerabilities? Excuse me. Sorry about that. So how do you find these vulnerabilities before the product gets into the hands of the customer? So we see even if you use all secure software engineering practices, vulnerabilities will still be present. And the only way to discover and remove these vulnerabilities from the product is to be able to do continuous testing at every step of the product life cycle. So we take a slightly different approach here to enable testing and do this testing continually through the life cycle of the product. So with a platform that we have, essentially you can do your testing during the development phase, where you can shift left your testing and so you can shift left your testing, and you can catch your vulnerabilities early before they become costly issues. You can do your testing during the integration phase and basically maintain security checks across all of your various interfaces during system integration. You can also do your testing during the testing and validation phase, and most importantly also during the production phase, where there's continuous monitoring to ensure that the ECUs are secure post-production as well. So these are different ways in the ways you can use the product. And here are some benefits before I wrap up. So basically, some of the big advantages: reusable testing scripts. So there's a wide array of testing scripts to test your low-level interface drivers. There's also a comprehensive suite for checking all of the communication protocols. There's ways tests to also check the secure access mechanisms And also there's cybersecurity tests to check for CVEs as well. And some big benefits here is long-term ECU monitoring, and you can do continuous monitoring to maintain ECU security over time. The nice thing about all of this is everything that gets executed is reviewable and accessible, and this way you can ensure compliance with some of the automotive standards and directives like ASPICE or the ISO SAE 21434 and the UNICE R155. So there's a lot of benefits, and essentially in conclusion, what we've seen here, that even though you have security mechanisms and if they have improved over the years, the complexity of the attacks have increased significantly, and hackers will continue to get ingenious in terms of trying to access the vehicle. What we also saw is just one wrong assumption can lead to security vulnerabilities. And here's also something which is important. Oftentimes we focus on the software, and even when the software developers make no mistake, I think what you saw in some of those examples is hardware attacks can be used to exploit the most secure software. So you've got to be cautious about that as well. So only with constant hardware in the loop testing, we can detect these vulnerabilities before the vehicle is actually delivered to the customer. So I'm going to wrap up there. And again, thank you all for watching. We are at booth 8, hall 1. And if you want to know more about the product, feel free to drop by, and we'll give you a demo of our product. And for those of you who don't know Lexington Soft, we are value-added resellers and have a lot of DevOps, DevSecOps, as well as embedded solutions, which are pretty tailored for the automotive space. So thank you, everyone, and really appreciate your time.